Exponential change with Newton's law of cooling. So this states that the cooling rate of a body is proportional to the difference between the temperature of the body and the surrounding environment. So how can we represent that with maths? Well, we can say that the rate of change of the temperature of the body is proportional, so factored in by K, to the difference between the temperature and the surrounding environment. And we put a negative here because it's cooling down, so we're cooling down. And this is essentially the relationship for Newton's law of cooling. And the best way to probably get into this is with an example. So let's have a look. Let's look at, we have a body initially has a temperature of 80 degrees. So let's write some of these things down. So initially means just T is 0. Its temperature of the body is 80 degrees. The temperature of its surroundings is 22 degrees. So this means E is going to be 22 degrees. This is Celsius. And we know that the body cools to 50 degrees Celsius in 5 minutes. So this is when T equals 5. And the first thing we want to find is the temperature of the body after 15 minutes, so when T equals 15. So in order to do this, we can use our initial equation here, and we need an expression for the temperature. So the first thing we'd like to do is to flip both sides of the equation. So we have d little t over d big T equals 1 over, we can say negative 1 over K times T minus E. And now we can go ahead and actually integrate both sides with respect to time, or one with respect to time and one with respect to temperature. The reason we can do that is if you like to think that we can multiply both sides by dt, where these dt's cancel out, and now we can just go ahead and integrate both sides. So we're going to integrate both sides. So we get the integral of d little t is just going to be t. And over here, let's take out the negative 1 on k, and we're left with 1 over t minus e dt. So we get t equals minus 1 on k, and we get, now the integral of 1 over t minus e, well, e is just a constant because we're deriving with respect to big T, and the derivative of big T is 1, and that's what we have on the numerator. So the integral of this is just going to be the ln of the absolute value of t minus e. And we know e is equal to 22, so we may as well throw it in. And we get plus a constant. But we need an expression for big T. So we're going to minus c from both sides. We get minus 1 on k, ln of t minus 22. Let's times both sides by negative k. So we're going to get minus k outside of t minus c equals ln of t minus 22. Let's raise both sides to the power of e. Let's take both sides and make them the powers of our base e. So we're going to have e to the minus k times t minus c equals e to the ln of t minus 22. The e and the ln will cancel out, so we just have t minus 22 equals e to the power of minus kt plus kc, so we just expanded here. Let's add the 22 to both sides. And I'm going to rewrite this as e to the minus kt times e to the kc, because this is just the reverse of our index laws. So when we're timesing with the same base, we add the powers together. And finally, we're just going to let, because e to the kc is just a constant, so we just may as well let that equal another constant. So we'll let a equal e to the kc. And then we finally get an expression for t being 22 plus a e to the minus kt. And we can go ahead and use that to find the values for t. But we're going to need to find a first before we do that, a and k. And we get some extra information to help us do this. So we know when the time is equal to 0, the temperature equals 80. So let's go ahead and use that information. So if the temperature equals 80, when the time is equal to 0, we'll have 22 plus a e to the minus k times 0. This is all going to be 1. So then we're just going to get a equaling 80 minus 22, which is going to give us 58. So we can now write our temperature is equal to 22 plus 58 e to the minus kt. But we still need to find value of k, and that's what this extra information was here for. We know that the temperature cools down to 50 degrees in 5 minutes. So let's go ahead and sub that information in. So we know it's 50 degrees when 5 minutes has passed, so we're going to sub in 5 for t. So we'll be left with that. We'll minus 22 from both sides. So we get 28 equals 58 e to the minus 5k. Divide both sides by 58. So we're just going to have e to the minus 5k equals 28 over 58. Let's take the natural log of both sides. So we're going to get ln of e to the minus 5k equals natural log of 28 over 58. This power will come down to the front, and then ln e will be 0. And then divide both sides by negative 5. So we're just going to get the ln of 28 over 58 divided by minus 5, which is roughly equal to 0.1456 to 4 decimal places. And we're going to go ahead and use that to finally find our T when, our temperature when time is 15. So this means our formula can now be written as T equals 22 plus 58 e to the minus 0.1456 T. And remember, we were after the temperature after 15 minutes. So big T when little t was 15. So we can just go ahead and substitute little t for 15. So we get 22 plus 58 e to the minus 0.1456 times 15. And all of that can just go in the calculator, and you'll get a temperature of about 28.53 degrees Celsius. So after 15 minutes, that's expected to cool down to that temperature. Second part of the question wants us to know the time taken, so little t, for the temperature to cool to 30 degrees. So that's when big T equals 30 degrees. So yeah, we can just go ahead and use our formula to substitute that in. So we'll have 30 equals 22 plus 58 e to the minus 0.1456 T. So we'll just minus 22 from both sides. So we'll get 8 equals 58, e to the minus 0.1456t. Divide both sides by 58. So we get 8 over 58 equals e to the minus 0.1456t. Take the natural log of both sides. So we'll get ln of 8 over 58 equals the ln of e to the minus 0.1456t. We can bring that power to the front. So we get minus 0.1456t. Then we just get the ln of e, which is 1. Finally, divide both sides by that decimal. So we'll just get t equals 8 over 58, the ln of 8 over 58 over minus 0.1456. And that's going to equal about 13.6 minutes. And if we were to graph this over time, we'd see we have our t-axis, our little t and our big T, and we had a starting temperature of 80 and the environmental temperature of 22, which actually acts as an asymptote, and this is an exponential function decaying towards that 22-degree value of the environment.